This video is on curvature, and this topic continues directly from the content from the last section on arc length and parameterization. To simply put, curvature is the measure of how curvy a curve is, or how sharp the turns are. Looking at the three curves, you may be able to visually tell that curve 2 is more curvy than curve 1, and that curve 3 isn't curvy at all. But how do we mathematically quantify curvature? If we look at this equation up here, curvature is represented with Greek letter kappa, and it equals the magnitude of dt ds. Remember that big T is the unit tangent vector, and s is the arc length, so it is the change of unit tangent vector t with respect to arc length s. If we go a little bit along the curve, how much do the unit tangent vectors change? Remember that unit tangent vectors have a fixed magnitude of 1, so the only part that can change about that vector is the direction they're pointing. Let's see how the unit tangent vectors change around the red points at each curve. For curve 1, if we go this much along the arc length, you can see how there is a slight change to the unit tangent vectors. Let's take a look at curve 2. Going along the arc length for curve 2, the direction these unit tangent vectors are pointing vary a lot more than they did for curve 1. So we could say that the curvature at this red point on curve 2 is greater than the curvature at this red point for curve 1. And then for curve 3 is actually a line, and the unit tangent vectors don't change at all. So along any point on a line, the curvature equals 0. Let's talk more about the initial formula we're given. Curvature equals the magnitude of dt ds. In Lagrange notation, this is the magnitude of t prime of s. The unit tangent vector is r prime over its magnitude. In this equation, because s, the arc length, is the parameter for r, the magnitude of r prime of s equals 1. So t of s equals r prime of s. If we take the derivative with respect to s, we'll have t prime of s equals r double prime of s. So we could say that the curvature equals the magnitude of r double prime of s. Now this is true only if r is in terms of s. This does not work if r is in terms of t. But remember, to get r in terms of s, we would have to reparameterize when we're usually given r of t. Sometimes we want to be able to find the curvature without having to reparameterize. So I'm going to show you some terms that curvature is also equal to. These are some terms that curvature is also equal to. I'm going to show you how we get each term, starting with the magnitude of dt ds. So we know that big T is a function of s, and s, the arc length, is a function of little t. If we want to take the derivative of the unit tangent big T with respect to little t, with the chain rule in Leibniz notation, this would be equal to d big T ds times ds d little t. Big T depends on s, and s depends on little t. We want the magnitude of dt ds, so let's take the magnitude of both sides. D big T ds is a vector, and this is multiplied by the scalar ds dt. So we can write the terms like this. The magnitude of d big T ds is what we want to isolate for. After dividing by the magnitude of ds dt, the magnitude of dt ds equals the magnitude of dt dt over the magnitude of ds dt. That's how we get this. Remember that ds dt is the speed, and speed is already non-negative, so we actually don't need to put these absolute value bars. And speed is also the magnitude of velocity, so ds dt equals the magnitude of v of t. For the denominator, we know that velocity equals the first derivative of r with respect to t, and then for the numerator, we're rewriting the derivative of unit tangent vector big T with respect to little t from Leibniz notation to Lagrange notation. From here, we can express curvature in terms of r and its derivatives. Before I start deriving this formula, we first need to understand that the unit tangent vector big T is orthogonal to its derivative. We know that the length or magnitude of the unit tangent vector big T is equal to 1. Let's square both sides. The magnitude of a vector squared is that vector dotted with itself. So the square of the magnitude of t can be rewritten as t dot t. Let's take the derivative of both sides. On the left side, we have the derivative over a dot product. This is the first vector dotted with the derivative of the second vector, added with the derivative of the first vector dotted with the second vector. And then on the right side, the derivative of a constant is just 0. The dot product is commutative, so t prime dot t is the same thing as t dot t prime. We can rewrite this whole left side as 2 times t dot t prime. Now let's divide both sides by 2, and we'll see that the dot product of t and t prime of t equals 0. And if the dot product of two vectors equals 0, that means that both vectors are orthogonal to each other. So t is orthogonal to t prime. We're going to need to remember this for later. As a matter of fact, if a vector has a constant magnitude, then that vector and its derivative are orthogonal to each other. This is because on the right side, we started with the magnitude of the vector. And if we take the derivative of a magnitude that is constant, that would equal 0. Now let's start deriving this formula. We know that the unit tangent vector equals r prime over its magnitude. In this formula, we have an r prime and an r double prime. So that's what we're going to try to find right now. If we isolate for r prime, we'll see that this equals the magnitude of r prime of t times t of t. The magnitude of r prime is the same thing as the magnitude of v, which is the speed, ds dt. That's r prime of t. Let's get r double prime of t. So let's take the derivative of both sides. On the left side, we have r double prime of t. On the right side, we have a scalar, and this is a vector. But they are both functions, and we're taking the derivative of the product of two functions. So we're going to use the product rule. So with the product rule, we have ds dt times the derivative of t of t plus the derivative of ds dt times t of t. So that's r prime and r double prime. Now in the numerator, we have the cross product between them. So let's find the cross product of r prime and r double prime. Here's r prime, here's r double prime. Here, we can use a cross product property. If we are taking the cross product between a vector u and the sum of two vectors v and w, we would have u cross v plus u cross w. Next, we're going to use another cross product property. R and S are scalars that are multiplying into their respective vectors u and v. And there's the cross product of ru and sv. What we can do is we can pull out the scalars r and s, and we can multiply that into the result of u cross v. In the green, we have ds dt, and that is a scalar. Multiplying ds dt with ds dt gives us the square of ds dt. And then we multiply that with t cross t prime. And then we do the same for the other side of the sum. Now, be careful. The square of ds dt is not the same thing as d2s dt squared. The first expression is the first derivative of s of t multiplied by itself. d2s dt squared is the second derivative of s of t. So right here we have t of t crossed with itself, and the cross product between two parallel vectors is the zero vector. So this entire side of the sum is wiped out. If you look back at the numerator for the formula of curvature, we want the magnitude of the cross product. So let's find that. ds dt, the speed is already non-negative, and on top of that, it's squared, so we don't need to put bars around this term. Now we need the magnitude of this cross product. Recall that the magnitude of the cross product of two vectors is the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between those two vectors. The magnitude of the unit tangent vector is 1, and the angle between t and t prime is 90 degrees. This is from knowing that t and t prime are orthogonal to each other. And then the sine of 90 degrees is just 1. And then ds dt can be rewritten as the magnitude of r prime. Now, if we isolate for the magnitude of t prime of t, we'll see that the magnitude of t prime of t equals the magnitude of the cross product of r prime of t and r double prime of t all over the magnitude of r prime of t squared. Let's go back to the curvature formula. Here's the magnitude of t prime of t, and that is divided by the magnitude of r prime of t. If we divide this term by the magnitude of r prime of t, then in the denominator we'll have the magnitude of r prime of t cubed. That's where this comes from. Let's do example 1. Find the curvature of r of t equals t squared t cubed at t equals 1. Let's use the curvature formula that we just derived. We're given r of t, and in this formula we need r prime of t and r double prime of t. So we need to take the first and second derivative of r of t. R prime of t is 1, 2t, 3t squared. And r double prime of t is 0, 2, 6t. Looking at the numerator of this curvature formula, we need to take the cross product of r prime and r double prime. So here's our determinant for the cross product. We have I hat, j hat, k hat in the first row. The first part of the cross product is r prime of t. So we put that in the second row of the determinant. The second part of the cross product is r double prime of t, and that goes in the last row. I'm going to go across the first row of the determinant. So starting with I hat, we have 2t times 6t minus 3t squared times 2. Next we have j hat, and we put a minus sign. We have 1 times 6t minus 3t squared times 0. And for k hat, we put a plus, 1 times 2 minus 2t times 0. Let's simplify. And here it is in component form. And now we take the magnitude of that cross product. We take each component, we square them, we sum them, we square root the sum. We can factor out a 4 inside the square root. And this is what we get for the magnitude of r prime of t cross r double prime of t. That's the numerator of the curvature formula. For the denominator, we need to find the magnitude of r prime of t and raise it to the third power. So that's the magnitude of r prime of t. Let's raise this to the third power. The square root of a term is the same thing as raising the term to the half power. and we can multiply the exponents. And this is the denominator of the curvature formula. Now we can evaluate the curvature of the curve at t equals 1. So plugging in a 1 for the t's here, we'll find that the curvature of r of t at t equals 1 is rad 19 over 7 rad 14. When you evaluate curvature at a t value, you don't have to find the curvature in terms of t and then plug in the value at the end. Another approach to this problem is to take the first and second derivative of r of t first, and after you find those, you can immediately plug in your t value. Then you can numerically take the cross product, magnitude, and divide. You can also solve it that way. Just make sure you find the derivatives before you plug in the t value. If the curve is in 2D, then we can use one of these two formulas. The formula on the left is helpful for if we have y as a function of x, and the formula on the right is if we have a vector valued function r. And then I'm going to use these in example 2, but they're pretty straightforward. So for example 2a, we want to find the curvature of the curve parameterized by r of t equals t sine of t. So we want to use the formula on the right in this case. Now remember, x equals f of t and y equals g of t. So in our example, x equals t and y equals sine of t. We are going to have to take the first and second derivative of x and y. The first derivative of x is x prime, this equals 1. The second derivative of x, x double prime, equals 0. Y prime equals cosine of t, and y double prime equals the negative sine of t. So curvature is going to equal, on the numerator we have the absolute value of x prime times y double prime minus y prime times x double prime. And this is over x prime squared plus y prime squared, quantity raised to the 3/2 power. This simplifies to the absolute value of negative sine of t over 1 plus cosine squared of t, quantity raised to 3/2. This function is curvature in terms of t, so we can write kappa of t, and then we can drop the negative sign inside of the absolute value. Let's do part B now. Find the curvature of y equals x squared at x equals 1. So this is y as a function of x, so we're going to use the formula on the left, and we need to find the first derivative and the second derivative of f of x. Y equals f of x, so f of x equals x squared. F prime of x is 2x, and f double prime of x is 2. So this is going to be curvature as a function of x now, and in the numerator we have the absolute value of f double prime of x, and in the denominator we have 1 plus f prime of x squared, and that sum is raised to the 3/2 power. And let's evaluate this at x equals 1. So the curvature of this curve at x equals 1 is 2 over 5 rad 5. For part B, we are given y as a function of x, but we can parameterize that and use the equation on the right if we want. Since y is a function of x, we can parameterize this by setting x equals to t, and this would mean y equals t squared. If we want to use the second equation, we'll need to get x prime, x double prime, and y double prime. We wanted to evaluate the curve at x equals 1. We have kappa as a function of t now. When we parameterize, we set x equals to t. And since x equals to 1, t equals 1. So evaluate this at t equals 1. And we get the same answer. Next, we're going to talk about the unit normal vector, and this is sometimes called the principal unit normal, or principal normal vector, the unit normal vector is orthogonal to the unit tangent vector, and like the unit tangent vector, the unit normal vector has a magnitude of 1. And this vector points in the direction that the curve is turning. So first, I'm going to draw the unit tangent vectors along this curve. In red, I'm going to draw the unit normal vectors, and like the unit tangent vectors, they should have the same length of 1. So the formula for the unit normal vector n is t prime of t over its magnitude. N is orthogonal to t, and remember from earlier we found how t is orthogonal to its own derivative, t prime. We divide t prime by its magnitude to get a unit vector. That's where this comes from. Another way we could get n is if we have r of t and we reparameterized it into r of s, and we have unit tangent vector t in terms of s. If we take the derivative of this, we'll have t prime of s. This is what dt ds is. So if you take the derivative of the unit tangent vector with respect to arc length s, and then you divide that by the curvature, then you'll have n as well. Let's rearrange this equation. dt ds equals kappa times n. This is the rate at which the unit tangents change as we go along the arc length. Kappa, the curvature, is a scalar, and then n is a vector with the magnitude of 1. Remember, at the beginning of this video, we said that the curvature equals the magnitude of dt ds. If we take away these magnitude bars, this is what we have. dt ds is a vector, and the unit normal vector n tells us the direction that vector points. The curvature kappa tells us the length of that vector. So I made a copy of the curve and cleaned it up a bit. Now I want to draw the dt ds vectors. We have the direction they point in from the unit normal vector n. We just need to multiply it by the curvature kappa. This will get the vector's length. Now, this drawing is not to scale. If we start at this point, there is some curvature, as we can see that there is change in the unit tangent vectors going along this region right here. So let's say this is dt ds for that point, and this is kappa times n. If we go along the curve this way, the curvature will decrease. As you can see, the unit tangent vectors aren't changing as much along this area. So the value for kappa will be lower around here. You can see how the length of dt ds gets shorter as we go along the curve. And then the direction the curve is turning changes. So that's the sense of what dt ds looks like, along with t and n. Let's do example 3. Find t, n, and kappa for the curve r of t. So for a, we have r of t equals 3t, 5 sine of t, and 5 cosine of t. Remember, the unit tangent t equals r prime of t over the magnitude of r prime of t. Alright, so first let's find r prime of t. Taking the derivative of r of t, we have 3, 5 cosine of t, negative 5 sine of t. And then its magnitude, square each component, sum them, square root the sum. And then we've seen this before. We can factor the 25 out, and we have cosine squared plus sine squared. Cosine squared and sine squared have the same argument inside, so this just becomes 25 times 1. So going back, we have 9 plus 25, or square root of 34. Alright, so we have r prime and a magnitude of r prime. So we can find our unit tangent now. There's r prime in the numerator. There's the magnitude of r prime in the denominator. I'm going to rewrite this as 1 over rad 34 times r prime of t, because this format is more beneficial to us as we work through the rest of the problem. The next thing we should solve for is the curvature, and let me bring up the formulas from earlier. We already know what the magnitude of r prime of t is, and we have t of t. The term that is best to find curvature given what we have right now is this one. From here, we can just take the derivative of unit tangent t and then take the magnitude of that. Let's take the derivative of t with respect to t. If we look at t, we don't need to take the 1 over rad 34 and multiply into each component to take the derivative. This is the coefficient, so we can take the derivative of each component by itself and then keep the coefficient where it is. Now this works specifically because 1 over rad 34 is a constant and there's no variables in it. If you're taking the derivative of a constant times a function, you can take the derivative of the function and then multiply the constant back in afterwards. That's the constant multiple rule. So taking the derivative of each component of t, the derivative of 3 is 0, the derivative of 5 cosine t is negative 5 sine t, and the derivative of negative 5 sine t is negative 5 cosine t. Now we need to take the magnitude of t prime. If you're wondering how to take the magnitude with the 1 over rad 34 in front, let me show you with variables. Let's say a is the 1 over rad 34, or any other constant that gets multiplied into this vector function. And then in each component, we have b, c, and d. If we were to multiply a in, we would have ab, ac, and ad. And if we were to take the magnitude of this, we square some square root. We can square each factor inside the parentheses individually, and then we can factor out the a squared. So taking the magnitude of t prime, like with a, the 1 over rad 34 gets squared, and then we multiply this to the sum of each component squared. 1 over rad 34 squared is 1 over rad 34, and then we have 25 sine squared plus 25 cosine squared. And then we can factor out the 25s, and in the parentheses we should be left with sine squared of t plus cosine squared of t. That is a 1. So we'll have square root of 25 over 34. We can square root the numerator and the denominator individually, so this is 5 over rad 34. That is the numerator for the curvature function, and then the magnitude of r prime is rad 34. Multiplying the numerator by the reciprocal of the denominator, we'll have 5 over 34. Then we need to find the unit normal vector n. N equals t prime over the magnitude of t prime. We have t prime and its magnitude. So there's t prime, and then we want to divide by the magnitude of t prime. This is the same thing as multiplying by the reciprocal of the magnitude of t prime. The reciprocal of 5 over rad 34 is rad 34 over 5. Now let me rearrange this. These rad 34s will cancel out, multiplying each component by 1 over 5. The 0 will stay at 0, this negative 5 becomes a negative 1, and this negative 5 becomes a negative 1. So there's t, kappa, and n. Okay, let's do part B now. First, the unit tangent vector t of t is equal to r prime of t over the magnitude of r prime of t. Let's find r prime of t. For the derivative of e to the t times sine of t, we're going to need to use the product rule. So we have e to the t times the derivative of sine of t, that is a cosine of t, plus the derivative of e to the t, which is e to the t, times sine of t. Next, we use the product rule for e to the t times cosine of t, and then the derivative of e to the t is e to the t. Now we take the magnitude of this. Let's square this term. The first part of the sum is e to the t times cosine of t, and squaring that we have e to the 2t times cosine squared of t, and then we add this to 2 times e to the t cosine of t times e to the t sine of t. e to the t times e to the t gives e to the 2t. Now we have a cosine times a sine. Plus, and then we square e to the t times sine of t. So e to the t times e to the t is e to the 2t. Now we have sine squared of t. Now we need to square this term. So first we square negative e to the t sine of t. Negative e to the t times a negative e to the t is a positive e to the 2t. And then we have sine squared of t. And then we add this to 2 times negative e to the t times sine of t times e to the t times cosine of t. The negative e to the t times the e to the t gives negative e to the 2t, and then we multiply the sine and cosine. We add this to the square of e to the t cosine of t, and then we add e to the 2t. Here we have 2 times e to the 2t cosine t sine t, and this term is a negative 2e to the 2t sine t cosine t. Adding both of these terms equals 0, so we can cancel them out. We can factor the e to the 2t's out. Cosine squared of t plus sine squared of t becomes a 1. So e to the 2t plus e to the 2t plus e to the 2t becomes 3e to the 2t. So then we get radical 3e to the 2t. And then we can pull an e to the t out of the square root. The magnitude of r prime of t is rad 3 times e to the t. So for the unit tangent vector t, like we did in part A, we can take the reciprocal of the magnitude of r prime of t and multiply that to the numerator. The reciprocal of the magnitude of r prime of t is 1 over square root of 3 times e to the t. And then here's r prime of t. Let's clean this up a little bit. In the first and second component of r prime of t, we have e to the t in both parts of the sum. And we have e to the t in the last component as well. Each component is getting divided by e to the t, so all those e to the t's will cancel out. So t of t should equal 1 over rad 3 times cosine of t plus sine of t, cosine of t minus sine of t, 1. Next, let's find the curvature. Kappa of t, we'll use the magnitude of t prime over the magnitude of r prime again. Let's find t prime. 1 over rad 3 stays in the front, and we take the derivative of each component. And then we take the magnitude of t prime. 1 over rad 3 needs to be squared, and then we multiply that to the sum of each term squared. 1 over rad 3 is squared, and it's already positive, so we can pull that out of the square root. Inside the square root, we are squaring this term. This becomes sine squared of t minus 2 times sine of t times cosine of t plus cosine squared of t. Then we add that to the square of this term. That becomes sine squared of t plus 2 sine t cosine t plus cosine squared of t. These two terms will cancel out. Inside both brackets, we're left with a sine squared of t plus cosine squared of t. And we should be left with a 1 in each bracket. So the magnitude of t prime of t equals rad 2 over rad 3. And this is the numerator of kappa of t. And we multiply this by the reciprocal of the magnitude of r prime of t. So curvature equals rad 2 over 3 e to the t. And then we have the normal vector n. This equals t prime of t over the magnitude of t prime of t. Here's t prime of t. We multiply this by the reciprocal of the magnitude of t prime of t. These rad 3's will cancel out. So n of t equals 1 over rad 2 times cosine of t minus sine of t, negative sine of t minus cosine of t, 0. Next, I want to talk about the curvature of a circle. And let's say that the circle has a radius of a. And to calculate the curvature, I'm going to use the same formula we used in example 3. First, we need to get r of t by parameterizing the circle. X equals the radius times cosine of t, and y equals the radius times the sine of t. So r of t equals a cosine of t, a sine of t. This circle is orientated in the counterclockwise direction. If you have a sine of t, a cosine of t, that's in the clockwise direction. But we're not going to be too concerned about the orientation when it comes to calculating the curvature. So r prime of t is negative a sine of t, a cosine of t. Now we need to take the magnitude of r prime of t. So in the first bracket we have a squared times sine squared, plus the second bracket is a squared cosine squared. We can factor out an a squared, and then sine squared of t plus cosine squared of t is a 1. So we have the square root of a squared times 1, or just a squared. This becomes the absolute value of a. The radius a should be a positive value, so we can just say the magnitude of r prime of t equals a. We have the denominator, let's get the numerator. First, let's get t of t. The unit tangent is r prime of t over the magnitude of r prime of t. Like before, I'm going to write 1 over the magnitude of r prime of t, which is a, and this gets multiplied with r of t, and then the a's will cancel. Next, we can find t prime of t. This is negative sine of t cosine of t, and then we take the magnitude of t prime of t. The magnitude of t prime of t is 1. Now we have what we need to find the curvature. Kappa equals the magnitude of t prime of t over the magnitude of r prime of t. The magnitude of t prime of t is 1, and the magnitude of r prime of t is a. The curvature for any circle is 1 over the radius. As you can see, there is no variable t in this equation. Regardless of what the parameter t is equal to, we're going to get this constant curvature at any point of the circle. So the curvature has an inverse relationship with the radius of a circle. The smaller the radius, the greater the curvature. The bigger the radius, the smaller the curvature. With the fact that a circle has constant curvature, a circle is useful in modeling curvature at a certain point on a curve. This leads us to the circle of curvature, or the osculating circle. At a point on a curve, the osculating circle is a circle that best fits the curve at that point. The osculating circle has the same curvature as the point on the curve. For a circle, we just found that the curvature is 1 over the radius. So the radius of the osculating circle, which is called the radius of curvature, is 1 over the curvature of the circle. This is represented with the Greek letter rho. Also at that point, the curve and the circle have the same unit tangent vector and the same unit normal vector. So here's the unit tangent vector at that point on the curve, and here's the unit normal vector. Now we find a point on the circle with the same t and n vector. So the point would be right about there. Then we match this point to the point on the curve, and the normal vector always points towards the center of the circle. That orange dot is the center of the osculating circle. Now, how do we find the center of the osculating circle? There is a vector c. This vector starts at the origin and terminates at the center of the osculating circle, and c equals r of t plus 1 over kappa times n. As you already know, r is a vector that starts from the origin and terminates at the point on the curve. Now from this point, we need a vector that goes along the direction of n to end at the center of the circle. The length we want this yellow vector to be is the radius of that circle, and that is rho, which is equal to 1 over kappa. So 1 over kappa scales the unit vector n and together they make up that yellow vector that starts from that point on the curve and ends at the center of the circle. So here's a curve, and on that curve there's points P1 and P2. Here's what the osculating circle looks like at point P1. Here's what the osculating circle looks like at point P2. There's more curvature at P1 than at P2. So the osculating circle at P1 should have a radius that's less than the osculating circle at P2. Example 4. Find the equation of the osculating circle for the curve y equals x squared at x equals 0. So this is a curve on a plane. In 2D, the equation of a circle is the square of x minus h plus the square of y minus k equals the radius squared. To plot the circle, we need to know the center and the radius. The center of the circle is h comma k, and since this is an osculating circle, rho is going to be the radius. To find the center of the osculating circle, we can use the equation c equals r plus 1 over kappa times n, and this is a vector equation parameterized by t. So we need to parameterize the curve y equals x squared. Since y is a function of x, we can set x equal to t, and y would equal t squared. And r of t equals t squared. Since we set x equal to t, when x equals 0, t equals 0. So to find the center of the osculating circle at x equals 0, we need to evaluate c at t equals 0. To find c at t equals 0, we need to find r of 0, kappa of 0, and n of 0. We can find r of 0 right now. That's just 0, 0. We also want to find curvature evaluated at t equals 0. For curvature as a function of t, I'm going to use the magnitude of t prime of t over the magnitude of r prime of t again. To find n, we need t prime and the magnitude of t prime. So if we solve for curvature with this formula, we'll find t prime and the magnitude of t prime within the process. So kappa of 0 equals the magnitude of t prime of 0 over the magnitude of r prime of 0. We can find the magnitude of r prime of 0 right now. R prime of t equals 1, 2t, so r prime of 0 equals 1, 0. And then the magnitude of r prime of 0 equals 1. We also want to know what the magnitude of t prime of 0 is. To get t prime, we need to find the function for t and take the derivative of it. And unit tangent vector t is r prime over the magnitude of r prime. R prime of t is 1, 2t. And we need the magnitude of r prime of t as a function. So we square each component of r prime of t, we sum them, and we square root the sum. So this is what t of t is. We are going to have to take the derivative of t, so I rewrote t like this, because I prefer to not use a quotient rule. So taking the derivative of t, we now have t prime of t. To get the first component, we bring down the exponent, and we subtract the exponent by 1, and apply the chain rule. For the second component, we have to use the product rule. So the first function times the derivative of the second function, which we bring down the exponent, reduced it by 1 again, and multiplied by the derivative of the base. And we add that to the derivative of the first function times the second function as is. So for our curvature function, let's evaluate t prime at t equals 0. And now we need to take the magnitude of t prime as 0. So now we know that the curvature at t equals 0 equals 2 over 1, or just 2. The last part of the formula is to find n. The unit normal vector equals t prime over the magnitude of t prime. So n of 0 equals t prime of 0 over the magnitude of t prime of 0. And by the way we found curvature earlier, here's t prime of 0, here's the magnitude of t prime of 0. So the unit normal vector n at t equals 0 is 0, 1. Now having r of 0, kappa of 0, and n of 0, we can find the center at t equals 0. So c of 0 equals 0, 1/2. So there's the curve y equals x squared on an xy plane, and here's the point at x equals 0 on the curve. C is 0, 1/2. So we start from the origin and we go up 1/2. That is the center of the osculating circle at t equals 0. The radius of the osculating circle rho equals 1 over the curvature. And at t equals 0, the curvature is 2. So the radius of the circle is 1/2. So the equation of the osculating circle for the curve y equals x squared at x equals 0 is x squared plus the square of y minus 1/2 equals 1 over 4. And in orange, here is the osculating circle at x equals 0. And now let me find the unit tangent vector at t equals 0 so I can plot t and n on the graph as well. Okay, so at x equals 0 or t equals 0, the unit tangent vector t is 1, 0. This points in the direction of motion at that point. And the unit normal vector is 0, 1. And this points towards the center of curvature.